Every year, over 3,000 tons of gold are mined worldwide. But you'll be surprised, a significant portion of this shiny treasure doesn't stay in mines or banks, but heads to a place where gold literally turns into art, Dubai. In a city that trades over $129 billion in gold annually, ingots become masterpieces that shine in the 300 shops of the legendary gold souk. What is really hidden behind the glitter of jewelry? Ancient rituals or cutting-edge technology? If you watch until the end, you'll discover a golden secret that almost no one knows. Our journey begins not in a luxury boutique, but in the bustling cargo terminal of Dubai's airport. It is here that tons of gold arrive from over 100 countries around the world, from distant mines in Africa, Australia, and America. These planes are not carrying passengers, but a precious cargo in the form of large, heavy ingots. Part of them is so-called doré gold, unrefined, with impurities of other metals, straight from the mines. Another part consists of standard bank ingots, but they all have a long path of transformation ahead of them. Dubai is not a mining location. It's a giant, incredibly powerful melting pot and production center, the largest gold hub on the planet. The first stop for our gold is a refinery. This is a true high-tech fortress, better protected than a bank. Here, the sacred act of purification takes place. Ingots are loaded into giant induction furnaces. The air is filled with a hum and heat. The temperature inside exceeds 1,900 degrees Fahrenheit, and the solid metal turns into a liquid, dazzlingly bright sun. The liquid gold boils, and impurities float to the surface, which are carefully skimmed off. But this is not enough to achieve perfect purity. Next, chemistry comes into play. The gold goes through complex electrolysis processes, such as the Miller and Woolwell processes, where an electric current and chemical reactions are used to remove absolutely all foreign metals. The goal is to achieve a purity of 999.9, so-called 4 nines, the highest standard in the world. At the output, we get ingots of pure, almost otherworldly gold, shining with a deep, rich yellow color. But surprisingly, jewelry is rarely made from such pure 24-karat gold. Why? Because it's too soft. A ring made of pure gold could be deformed by a simple handshake. And this is where true jewelry science begins. To make gold strong and give it different shades, it is alloyed with other metals. This process is called alloying. Pure gold is melted again, and a strictly measured amount of ligature, an alloy of copper, silver, palladium, or zinc, is added to it. Do you want the classic yellow gold, so beloved in the East? Add a little silver and copper. Dreaming of romantic rose gold? Increase the share of copper. And for elegant white gold, palladium or nickel is needed. This is how different purities, or carats, are born. In the Dubai market, the most popular are 22 carats. This is 91.6% pure gold and 18 carats. That's 75% pure gold, which are the perfect compromise between purity and practicality. Now that we have a gold alloy of the desired color and strength, the most interesting part begins, the creation of the jewelry itself. And here, Dubai demonstrates all its versatility, combining futuristic technologies with a craft that is thousands of years old. Many pieces begin their life on a computer screen. Jewelry designers create complex three-dimensional models using CAD software. They can draw every detail, every swirl of a future necklace or earrings. Then this digital model is sent to a 3D printer, which, not from plastic, but from a special wax, grows a precise copy of the jewelry layer by layer. It's a wax wonder. Next, this wax model, or wax pattern, becomes the basis for casting. It is dipped into a special plaster-like mixture that hardens, forming a mold. Then this mold is heated. The wax melts out, leaving behind a perfectly accurate hollow impression of the future jewelry. And here it is, the moment of truth. Molten, red-hot gold is poured into this mold under pressure, or with the help of a vacuum. Every minute detail, reproduced with computer accuracy, is filled. When the metal solidifies, the plaster mold is broken, and a rough gold piece is born. But this is just a skeleton. Now master jewelers, whose skills have been passed down from generation to generation, get to work. They grind, polish, assemble individual parts, turning metal into a work of art. Imagine these workshops filled with the buzzing of drills, the quiet tapping of hammers, and the focused faces of the masters. They use techniques that haven't changed for centuries, creating the finest patterns from wire, inlaying pieces with precious stones, engraving complex Arabic ornaments. This is painstaking manual labor that requires incredible skill and patience. Each stone is set by hand, each link of a chain is checked for strength, and, of course, quality control. The government of Dubai is extremely strict about the reputation of its main market. Every piece undergoes a mandatory check in the municipal laboratory. A special hallmark is stamped on it, confirming the carat. This is a guarantee of authenticity. You will never buy a fake in an official Dubai store. This strict control system has created the city's reputation as the most reliable place to buy gold in the world. And so, having gone through this long and complex path, a piece of gold jewelry ends up in the window of one of the more than 380 shops of the legendary gold souk in the Dera district. This is a place where history meets luxury. A market that started in the 1940s as a small group of merchants from India and Iran has turned into a global center of attraction for everyone who appreciates the beauty of gold. Here you can see everything, from modest chains to giant wedding necklaces weighing several pounds, from classic Arabic designs to ultra-modern European styles. The air here is thick with the excitement of bargaining and the enthusiastic exclamations of tourists. This is not just a market, it's a show, an attraction, an open-air museum. This is the journey of gold in Dubai. From a formless piece of metal, mined thousands of miles away, through the fire of furnaces and the hands of talented masters, to a dazzling masterpiece waiting for its owner in the world's capital of glitter. It's a process where modern technologies serve ancient art and strict control guarantees quality. And all this to maintain the loud and absolutely deserved title, City of Gold. Incredible, isn't it? Dubai has firmly established itself as one of the leading global gold trading centers, ranking second in the world in 2023 by trade volume, surpassing the United Kingdom. The total value of gold trade in the UAE that year exceeded 129 billion US dollars, which is 36% more than in the previous year. This highlights the rapid growth and strategic importance of the emirate in the global precious metals industry. Between 20 and 30% of the entire world's gold circulation passes through Dubai annually. Gold trade accounts for almost 30% of the UAE's total non-oil exports, which indicates a successful diversification of the economy. Last year, over 5,400,000 contracts were concluded on the Dubai Gold and Commodities Exchange for a total amount of over $1 billion, $115 billion. Gold and silver futures amounted to 80,000 contracts for a total of over $44 million. The dynamics of the gold market in Dubai are influenced by global economic uncertainty, fluctuations in the US dollar exchange rate, to which the UAE dirham is pegged, and stable demand from investors and consumers. In times of instability, gold is traditionally seen as a safe haven asset for investment. Analysts predict further market growth. The gold bullion market in the UAE is expected to grow at an average annual growth rate of almost 10% until 2031. This will be facilitated by a business-friendly regulatory environment, a developed logistics infrastructure, and the absence of value-added tax on gold. The UAE's entry into BRICS Plus in 2024 opens up new opportunities for expanding gold trade with other market giants. Imagine this. Every year, the world cranks out over 100 million tons of nuts and bolts, the invisible heroes of our industrial world. They hold together our bridges, our planes, our ships, and even our tallest skyscrapers. But few people know that behind every single one lies a process with precision down to 1,000th of an inch. We're talking metal cleaned in acid, forged under massive presses, hardened at over 2,000 degrees, and tested to its breaking point. So what makes an ordinary bolt strong enough to hold hundreds of tons? Stick around, and you'll learn the secret that turns a simple piece of steel into a part the whole world depends on. A high-volume nut and bolt plant isn't just a factory. It's a high-tech powerhouse where raw steel becomes the hardware that holds our world together. The whole thing is a complex, multi-stage marathon of machining, stamping, heat treating, and non-stop quality control. It all starts with the raw material. High-quality steel wire rod comes in, but it's dirty. First, it needs a serious cleaning to get rid of rust and scale. The most common way to do that? A chemical bath. We're talking a process called acid pickling, where the steel gets a dip in sulfuric or hydrochloric acid. This stuff eats away all the grime, leaving the metal surface perfectly clean and ready for what's next. After the acid bath, the wire is thoroughly rinsed with fresh water to get every last drop of acid off. Then it's dried. For an even deeper clean, some plants use sandblasting or mechanical grinding. You might even see a process called electro-cleaning, which zaps the surface to level it out and boost its rust resistance. On the big production lines, they combine everything: mechanical scrubbing, a chemical dip, a rinse, and a dry. And they don't just eyeball it. Quality control uses visual checks and special instruments to make sure that surface is perfectly clean. Before it moves on, the metal gets a temporary rust preventive coating to keep it pristine during storage and handling. The main ways to make a bolt are cold forming and turning. Cold forming is the real workhorse here. That's where a machine takes the metal wire and shapes it under massive pressure, all without heat. The wire feeds through a series of dies that hammer it into the shape of a bolt. First, the round shank, then the head, usually a hex head so you can get a wrench on it. The beauty of cold forming is that it's incredibly precise, makes the steel stronger, and wastes almost no material. Once the head and body are formed, it's time for the threads. Here, they use a method called thread rolling. Instead of cutting the threads, the bolt blank is forced between special dies that literally press the threads into the metal. This process makes the threads incredibly strong and durable. Some of these high-speed lines can churn out hundreds of bolts a minute. For nuts, they often use hot forging. Steel blanks are heated up to a blistering 2,200 degrees Fahrenheit. That's about 1,200 Celsius, making the metal soft and pliable. Then, a press forges the iconic hex shape. After that, a hole is punched through the middle, and the internal threads are cut on special machines called tappers. Just like bolts, nuts go through heat treatment to make them tough and wear-resistant. Heat treating is where a bolt gets its backbone. It's a two-step process: quenching and tempering. First, in quenching, the bolts are heated up and then rapidly cooled. This makes the steel incredibly hard, but also brittle. So the next step is tempering. They're reheated to a lower temperature, which gets rid of the brittleness but keeps all that strength. This is how bolts get their specific grade or property class. After heat treating, every batch goes through brutal quality control. Sample bolts are checked for size, strength, thread accuracy, and any surface defects. We're talking micrometers, go-no-go gauges, and special optical sorters. Any parts that are out of spec are either rejected or sent back for reprocessing. To fight off rust, most bolts and nuts get a protective coating. This could be zinc plating, hot dip galvanizing, or special zinc flake coatings. This is what keeps them from rusting away, especially out in the elements. The finished products are then sorted by size and strength, boxed up, and prepped for shipping. Modern plants have automated lines cranking out hundreds of thousands of these a day. The parts travel on conveyors to automatic sorting machines that use optical sensors to check every last one. Anything that's damaged or not up to snuff gets kicked out. This makes sure only top quality hardware makes it to the packaging line. From there, the nuts and bolts go into automated bagging lines with inline scales and counters that measure out the exact quantity for each package. This could be small plastic bags, cardboard boxes, or bulk bins, depending on what the customer needs. The packages are labeled with all the key info: size, grade, manufacturer, and date. For big industrial orders, they're often packed in bulk bags or large containers to make shipping and storage easier. The whole process is automated to ensure the packaging is sealed tight to keep out moisture, dust, and prevent any damage in transit. Even though most of it is automated, there's still a human touch. For special kits or custom orders, workers will manually check the quality of the packaging, assemble the right mix of nuts and bolts, box them up, and get them ready to ship out. This flexibility allows them to meet specific customer needs with pinpoint accuracy. After packaging, the products go through one last check to make sure the labels are right and the packages are sealed. Then, they're sorted in the warehouse by order and prepped for dispatch. And it's not just standard stuff. Many plants also make custom fasteners based on a customer's specific blueprints, which is crucial for specialized industries like aerospace, automotive, or heavy construction. The global market for fasteners is on a steady climb, and it's all driven by a few key things. First up, construction. As countries spend more on infrastructure, we're talking bridges, roads, and new buildings, the demand for these steel connectors goes through the roof. Second, the automotive and machinery industries. Every car, truck, and piece of factory equipment is held together by hundreds of high-quality fasteners. As those industries grow, so does the need for top-grade nuts and bolts. For example, in Europe, car production is expected to climb, which directly boosts the demand for metal products, including fasteners. At the same time, the steel industry itself is getting smarter, using digital tech and automation to produce better, more specialized products. Of course, the cost of raw materials like iron ore and energy can affect things. But at the end of the day, as long as we're building, driving, and manufacturing, the demand for nuts and bolts isn't going anywhere. Imagine this, a single piece of steel that can hold the weight of 100 fully loaded semi-trucks. How? It's all about a shape engineers call the I-beam. This isn't just metal, it's the backbone of our cities, born from rusted scrap and forged in lightning, fire, and thousands of tons of pressure. But here's the kicker. Why are brand new I-beams almost entirely made of the past? Cars from the 70s, rails from the 30s, even armor from World War II. All of it could be holding up a modern skyscraper. Stick around and you'll learn a secret that will change the way you think about the power of steel. The genius of the I-beam is its shape. The real heavy lifting is carried by the top and bottom parts, so that's where most of the metal is packed, in the flanges. The thin web in the middle just keeps them locked in place. This gives you maximum strength for minimum weight. And that strength is just insane. A single heavy I-beam, set up right, can handle loads of hundreds of thousands, sometimes even millions of pounds. Picture a whole line of fully loaded semi-trucks, all parked on one single piece of steel. That's real power. This story doesn't start in some shiny workshop. It starts in a massive, rusty, noisy yard that looks like a graveyard for metal giants. This is a scrap yard. Mountains of old cars, chopped up rail cars, building frames, and industrial junk are all waiting for a second chance. A giant crane with a powerful electromagnet drops down on the pile, and with a metallic groan, tons of old iron leap up to meet it. This scrap is the main ingredient. It gets loaded into a huge steel basket and sent to the melt shop for its trial by fire. Steel is the undisputed champion of recycling. The recycling rate for structural steel in the US is a whopping 98%. That means nearly every piece of steel from torn down buildings, old bridges, and scrapped ships gets put back to work. On average, a new I-beam made today is 90% recycled metal. This creates an incredible, endless loop. A skyscraper going up today could have a piece of a 70s muscle car, a 1930s railroad track, and even armor from a World War II battleship inside it. This isn't just a hunk of steel. It's concentrated history, melted down and reborn for a new tour of duty. So these numbers aren't just stats. They're the silent language our cities are built on, a language of strength, efficiency, and the almost endless life of metal. Every year, the United States cranks out over 5 million tons of structural steel, and the lion's share of that is I-beams. That's a number so big, it's hard to get your head around. Let's try. The steel in the famous Golden Gate Bridge weighs about 83,000 tons. That means, in 1 year, American mills produce enough beams to build over 60 Golden Gate bridges. The heart of the plant is the electric arc furnace, a giant kettle, the size of a small house, where our scrap metal is dumped with a thunderous crash. 3 massive graphite electrodes, thick as ancient trees, are lowered in from the top. And then the operator hits the juice. An electric arc, basically a man-made lightning bolt, erupts between the electrode tips and the metal with incredible force. The shop fills with a deep, bone-rattling roar, and the light from the arc is blinding. The temperature inside instantly shoots up to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts to melt, turning into a boiling, blazing lake of steel. Special additives are tossed into this molten bath to get the exact grade of steel needed, strong but flexible enough to handle massive loads. When the steel is ready, it's time to turn this liquid river into something solid. The molten metal is poured into a continuous casting machine. The blazing liquid flows into a special, water-cooled copper mold. As it passes through, the outer layer of steel freezes, forming a thin skin. Next, this still mushy on the inside ingot is continuously pulled downwards through a chamber of water spray where hundreds of nozzles blast it, forcing it to solidify all the way through. What crawls out of the machine is an endless, glowing red, massive steel billet. This is called a bloom. Automated torches hiss to life and slice off pieces to the right length, say 20 or 30 feet. This is our blank, our piece of dough that we're about to shape into a beam. These hot, but now solid blooms are sent to the next furnace, the reheating furnace. It's like a giant tunnel with a fire roaring inside. The blank moves slowly through it, where its temperature is cranked back up to the perfect working heat, around 2,200 degrees Fahrenheit. It becomes soft and pliable, like clay, ready for the most important step, rolling. And this is where the real show begins. The bloom, glowing a brilliant orange, rolls out of the furnace and hits the rolling mill. This is a series of giant steel rollers, like massive rolling pins, lined up one after another. But these rollers aren't flat. They have special grooves cut into them, shaped to gradually form an I-beam. The bloom slams into the first set of rollers. they squeeze it with thousands of tons of force, making it a little thinner and longer. Out the other side, it's grabbed by the neck set, which squeezes it from a different angle, starting to form the flanges and the web of the future beam. And so, step by step, passing through dozens of these roller sets, our shapeless billet is stretched and molded, taking on that familiar eye shape right before your eyes. It's an incredible sight. A piece of glowing steel that started at 20 feet long gets stretched into a fiery ribbon hundreds of feet long. The whole mill is filled with a symphony of bangs, screeches, and the hiss of water keeping the rollers cool. When the beam exits the final, finishing roller, it has the perfect shape and dimensions, down to a fraction of an inch. Hot, long, like a fire serpent, it travels down a roller conveyor to a massive cooling bed. This is a giant rack where the beam slowly cools, letting its heat radiate into the air. As it cools, the metal shrinks a bit, and sometimes the beam can get a slight warp. To fix that, after it's cooled down, it's sent to a straightener. This thing is like a giant steel chiropractor, passing the beam through a set of rollers that align it until it's perfectly straight. So, we have a perfectly straight, long beam, but it's not ready to ship yet. Time for the finishing touches. First, it's cut to the specific lengths the customer ordered. This is done by giant saws with blades 6 or 7 feet across. With a deafening scream and a shower of sparks, the saw cuts through the thick steel in seconds. Then, every single beam goes through a tough quality control check. Inspectors measure its geometry, and special ultrasonic machines scan the metal to make sure there are no hidden cracks or flaws inside. Only then does the beam get its marking, its birth certificate, with the steel grade, size, and batch number. The finished inspected beams are picked up by giant cranes and stacked in the yard, or loaded directly onto special railcars or trucks. And just like that, this steel backbone, born from rusty scrap, forged through fire and pressure, is ready to ship out to a job site, to become the silent but incredibly strong skeleton for a skyscraper that will scrape the clouds, or a bridge that will connect two shores. Standard beams on a construction site can be anywhere from a few inches to 3 feet tall. But then there are the real monsters, the so-called jumbo sections, used in the most critical spots of skyscrapers. Their height can be over 4 feet, and their weight is something else. The heaviest ones can weigh over 800 pounds per foot. Think about that. Every foot of that beam weighs as much as 3 grown men. And a standard length for these things is 60, 80, or even 120 feet. A single one of those beams can weigh as much as a battle tank. Imagine a metal that's lighter than steel, stronger than aluminium, and can withstand temperatures at which other materials simply burn up. A metal used to build aircraft that conquer space and implants that serve people for a lifetime. Sounds like science fiction? But this is titanium, one of the most mysterious metals on Earth. It starts with tiny grains of ilmenite and rutile, and ends up as parts for supersonic jets and spacecraft. But few people know. Behind the gleam of titanium lies a manufacturing secret so dangerous and energy intensive that it's rarely spoken of. If you watch till the end, you'll learn something that will forever change your perception of this metal. The story of titanium production begins in the late 18th century when, in 1791, a British clergyman and amateur mineralogist named William Gregor discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, the pure metal was first successfully isolated only in 1825 by the Swedish chemist Berzelius, though at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and the real breakthrough came in 1925 when Dutch scientists Van Arkel and de Boer developed a method for producing high-purity titanium, paving the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the USA, where the metal became indispensable in aviation, the space industry, and military applications. The production of titanium starts with the mining of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in placer or lode deposits and are widespread across the globe, particularly in Australia, Canada, China, Norway, and South Africa. After mining, the ore undergoes a complex multi-stage processing. First, it is enriched, separating the titanium minerals from the waste rock to obtain ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, the titanium tetrachloride is reduced with magnesium or sodium in special reactors at high temperatures in an inert atmosphere, producing titanium sponge, a porous metallic powder. This titanium sponge is then pressed, melted, and cast to obtain ingots or billets for further processing. The production of titanium is energy-intensive and expensive due to the complexity of the technological processes and the need to work in high-purity conditions. The main industrial method for producing titanium is the Kroll process, which remains the global standard. It involves the chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, allowing for the production of high-quality metal for aviation, space technology, medicine, and other industries. Thus, titanium production begins with the mining of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex, multi-step technological process that begins with the extraction and preparation of titanium-bearing raw materials, mainly ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. To do this, the titanium ore concentrates are chlorinated in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and chlorine gas react with the raw material to form titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation to obtain high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at high temperature. The result is titanium sponge, a porous metallic powder containing impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the titanium sponge is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used to produce alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is titanium sponge. It looks nothing like a regular metal bar, but more like a piece of metallic sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First and foremost, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that enhance its properties. To obtain an alloy, alloying elements are added to the molten titanium, most often aluminium, vanadium, molybdenum, iron, or niobium. These additives change the metal's structure, increasing its strength, heat resistance, corrosion resistance, and improving its workability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, after which it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more malleable and are passed through special rollers. Rolling allows for reducing the metal's thickness, giving it the desired shape and size, as well as improving its structure and mechanical properties. The result is various types of rolled products: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. From these rolled products, sheet metal is made: thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are distinguished by their high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and its alloys are used. These can include mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometries that are impossible to produce with traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are required. Furthermore, to enhance their performance characteristics, titanium products can undergo heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used for 15% of the weight of a modern passenger aircraft, significantly reducing its overall weight and increasing fuel efficiency. In the medical field, about 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability. Every year, over 4 billion miles of fiber optic cables are produced worldwide. That's enough to wrap around the Earth more than 160 times. But few people know that their journey begins with sand. A special kind, whose purity is measured in parts per million. Because even one microcrack can destroy a signal that's racing for thousands of miles at the speed of light. What is this magic? How does ordinary sand turn into transparent threads, thinner than a hair, but stronger than steel? Watch closely. At the end of this video, you'll learn a secret you've never heard before. To create a thread capable of transmitting light at a speed of over 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, which means in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, and air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop, and all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one micro scratch can cost you signal quality. A large, transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod, and this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break. Cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube, or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin, or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire, so the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe, resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. Every year, billions of square feet of concrete are born in the world, but only a few know about the material that has turned construction on its head. Imagine this. In a single shift, one machine can create almost half a mile of slabs, and the annual output in North America is over 200 million square feet. That's the area of 30 pentagons. How do these lightweight slabs, weighing thousands of tons less, support entire buildings? The secret is hidden in their steel muscles and the mysterious voids inside. Watch till the end, and you'll discover something most people don't even have a clue about. The slip former machine crawls along a 600-foot casting bed at a speed of about 4 feet per minute. Doesn't sound too quick? Well, let's do the maths. That's 200 feet an hour. That's almost the length of an Olympic swimming pool, born from concrete in less than an hour. In a single 10-hour shift, one of these beds can churn out nearly half a mile of perfectly formed concrete slab. And a big plant might have several of these beds. This isn't just building, it's a conveyor belt running at a speed unthinkable for traditional, pour-on-site concrete. And now for the main trick, the hollow cores. These holes inside aren't just for looks. They slash the slab's weight by almost 50% compared to a solid slab of the same thickness and strength. What's the payoff? Picture this. You're building a 100,000 square foot office block. If the floors were made from standard, solid concrete, they'd weigh about 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just stripped 2,000 tons of dead weight from the building. That's the weight of about 500 adult elephants that the foundations, columns, and beams no longer have to carry. This allows the entire structure to be lighter, more slender, and most importantly, a whole lot cheaper. But how can such a light slab be so strong? The secret is in those tensioned steel muscles. The concrete used in these slabs isn't what you'd find on the footpath. It's high-strength concrete that can handle pressures over 8,000 pounds per square inch, while standard concrete manages only 3,000 or 4,000. And the steel strands inside are tensioned with such force that they create a constant state of compression within the slab. Because of this, a hollow core slab can easily span 60 feet with no intermediate support at all. 60 feet. That's the width of a professional basketball court. Imagine a huge open space with not a single column in sight. That's exactly why these slabs are a favorite for building car parks, supermarkets, and open-plan offices. Every year, over 200 million square feet of hollow core slabs are produced in North America. The number is just staggering. It's enough area to build 30 colossal buildings like the Pentagon. Every single year. This isn't just a building material. It's an entire industry built on speed, efficiency, and clever use of resources. So these figures aren't just dry data. They're proof that sometimes, to get stronger, you just have to get rid of the unnecessary stuff on the inside. It all starts not in a concrete mixer, but on a massive, perfectly flat runway inside the workshop. This is the casting bed. Imagine a perfectly smooth, polished steel track a few feet wide, but 600 feet long. That's longer than 2 footy fields, end to end. Beneath this track run, pipes circulating hot water or steam to keep it warm. This is the perfect cradle for the birth of our future giant. At both ends of this track stand massive steel abutments, anchored into a thick concrete foundation. They're like steel teeth sunk into the earth, and their job is to withstand simply inhuman loads. Between these two abutments, high-strength steel strands are stretched. This isn't your average wire. It's several steel filaments twisted together, each capable of holding the weight of a car. They are laid out along the entire 600-foot length of the bed, forming the slab's future skeleton. One end of each strand is securely fixed in an abutment. The other is hooked up to a giant hydraulic jack, and this jack starts to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. That's like hanging 3 full-sized utes off each thin strand. The steel muscles tense up, becoming as taut as the strings of a giant guitar, storing a colossal amount of energy. This is secret number 1, pre-stressing. When the steel skeleton is strained and singing with tension, the star of the show appears, the slip former. This is one of the most incredible machines in the construction world. Imagine a strange, low-slung, self-propelled creature, slowly crawling on rails along our long bed. It has a large hopper on top, which is filled with concrete. But this isn't your typical liquid concrete. It's what's known as zero-slump concrete. It's so dry it looks like damp earth. If you picked it up, it wouldn't flow through your fingers. And so, this machine begins its slow journey. Inside, a real marvel takes place. Firstly, the concrete from the hopper is fed downwards, enveloping our tensioned steel strands. Secondly, special vibrators and compactors ram this dry mix with incredible force, making it unbelievably dense. And thirdly, and most importantly, inside the machine are special forming tubes, or mandrels, which vibrate as they push through the concrete, leaving behind perfectly round, smooth voids. The machine, like a giant concrete snail, slowly crawls forward, leaving in its wake a perfectly formed, endless concrete slab with hollow cores inside and tensioned steel muscles hidden within its body. Because the concrete is so dry, it holds its shape instantly and doesn't sag. This is secret number 2. The voids, which make the slab 50% lighter than a solid one while barely reducing its strength, as the top and bottom sections do most of the work. Once the machine crawls to the end of the 600-foot bed, its job is done. But our slab is still green and weak. It's time for a spa treatment. Workers cover the entire length of this concrete ribbon with huge insulating tarps, like blankets. Hot steam is then pumped under these blankets. This creates a sauna effect, which dramatically speeds up the chemical reaction of the concrete curing. Under normal conditions, concrete needs weeks to reach its full strength. But in this hot, humid atmosphere, it achieves the required strength of over 5,000 pounds per square inch in just 12 to 24 hours. When the concrete has set and become hard as rock, it's time for the release. Workers slowly let off the pressure on the hydraulic jacks. The tensioned steel strands, now permanently bonded to the concrete, try to shrink back to their original length. But the concrete won't let them. As a result, this massive compressive force is transferred to the concrete slab itself. Now it's not just a concrete slab, it's pre-stressed or compressed. This means that when a load from above tries to bend it, it first has to overcome this built-in compressive force. This is what allows it to span huge distances without extra support. And the final act of this performance, the cutting. A giant saw travels on rails along our long concrete ribbon. It's a monster with a massive blade coated in industrial diamonds. With a deafening roar and a spray of sparks and cooling water, this saw cuts the slab with incredible precision into sections of the required length, according to the order. The finished, perfectly flat, lightweight, and incredibly strong slabs are then picked up by giant cranes and loaded onto trucks. And just like that, after a journey from a tensioned steel string to the slow crawl of a concrete snail and a final diamond cut, this brilliant piece of engineering is born, ready to become the fast, efficient, and reliable flooring in the buildings where we live, work, and play. Every year, billions of square feet of drywall are produced worldwide. In the United States alone, over 27 billion. That's enough to lay a 3-foot wide path from the Earth to the Moon, and still have enough for halfway back. Imagine millions of tons of stone being transformed into the smooth walls of our homes. But the real secret begins where ordinary gray stone becomes a thirsty powder, a material that can miraculously turn back into stone. Watch closely. At the end, you will discover a secret that most people have never even guessed. The numbers behind drywall production in the United States are not just big, they are astronomical, and they tell a story of how the country builds, renovates, and breathes. In a recent year, factories in the US produced approximately 27 billion square feet of drywall panels. This number is so colossal that it's hard to comprehend. Try to imagine. If you were to lay out all this amount of drywall, you could create a continuous 3-foot wide path that would stretch from the Earth to the Moon and almost halfway back. Or, with this number of sheets, you could completely cover the entire territory of the state of Delaware twice, and still have some left over. This endless stream of building material is not only a physical product, but also a powerful economic indicator. The market for these panels in the US is valued in the tens of billions of dollars, reflecting not just the cost of the material itself, but also thousands of jobs in mines and factories, in logistics and construction. It all begins not in a workshop, but much earlier, in a quarry where gypsum is mined. This is a natural mineral, a stone that formed millions of years ago from ancient seas. It can be white, grayish, sometimes with pink veins. Huge excavators dig into the gypsum deposits and load dump trucks with boulders of this stone. These trucks bring tons of gypsum to the factory and dump it onto the raw material yard, creating entire mountains waiting for their transformation. The first stage inside the factory is coarse crushing. The gypsum boulders fall into the giant steel jaws of a primary crusher. With a deafening roar and grinding, the machine breaks the large stones into smaller pieces, the size of a fist. This is just the beginning. Then this crushed gypsum is fed by a conveyor belt to secondary mills. Here, dozens of steel hammers, rotating at an insane speed, break these pieces into even smaller fractions, turning them into something like coarse gravel. But even this is not enough. The final stage of grinding turns the gypsum into a fine, powder-like dust. It becomes so fine that it resembles flour or dust. This powder is the main raw material, but it still hides a secret that needs to be revealed. The next step is one of the most important and interesting. It's a process called calcination, and in essence, it's the controlled drying of gypsum. The thing is, in the crystalline structure of natural gypsum, water molecules are locked in. For drywall to be able to harden, this water must be temporarily driven out. To do this, the white powder is fed into a huge, slowly rotating kiln. It looks like a giant drum, tilted at a slight angle. Inside this kiln, a very precise temperature is maintained, around 300 degrees Fahrenheit. The gypsum powder, slowly tumbling inside the drum, heats up, and the water bound to it turns into steam and evaporates. Chemically speaking, gypsum turns into calcium sulfate hemihydrate, but to put it simply, it becomes thirsty. Now this powder, which is now called plaster of Paris or stucco, has a unique property. If you add water to it again, it will greedily absorb it and turn back into a hard gypsum stone. It is this property that lies at the heart of the entire production process. The resulting hot powder is cooled and stored in giant silos, resembling towers, from where it will be fed to the main production line. And now the most spectacular part begins, the creation of the sheet itself. In the workshop, there is a huge conveyor, hundreds of feet long. At its beginning stand two giant rolls of special dense paper, or paperboard. One roll is for the face side. It is perfectly smooth and white. The other is for the back side. It can be a bit darker and grayish. The ribbon from the bottom roll, the face side, is unwound and laid on the conveyor, forming an endless track. In parallel with this, in a giant mixer resembling an industrial food processor, the core is prepared. Our thirsty gypsum powder, water, and a whole cocktail of various additives are continuously fed into it. Each additive plays its own role. Foaming agents make the gypsum mass lighter and more porous, like whipped cream, to reduce the weight of the sheet. Plasticizers make the mixture more fluid, so it spreads evenly. Accelerators or retarders allow engineers to perfectly control the time it takes for the gypsum to set. Starch helps the gypsum core to better adhere to the paper covering, and fiberglass adds strength. This mixture, called a slurry, resembles a thick grey porridge. It is poured in a continuous stream directly onto the paper ribbon, moving on the conveyor. Special devices evenly distribute this mass across the entire width of the paper. The edges of the bottom sheet of paper are neatly folded upwards, forming the sides of the future sheet. And at this moment, the second ribbon of paper from the back roll is laid on top, like a lid. The result is an endless, perfectly even sandwich. Paper, gypsum mass, paper. This sandwich immediately passes between two rollers or under a forming plate, which compress it to a precisely specified thickness, for example, ½ an inch. The newly formed, still soft and wet sheet of drywall continues its journey on a very long conveyor, which is called the setting line. Its length can reach several hundred feet. As the sheet slowly moves, a real miracle happens inside it. The gypsum powder reacts with water. The rehydration reaction takes place. The gypsum turns back into a hard stone, releasing heat in the process. If you touch the sheet at this stage, it will be warm. In a few minutes, the loose mass becomes hard enough to hold its shape. At the end of this long line stands a flying knife. This is a huge blade that moves in sync with the belt, and at the right moment makes a quick, precise cut, slicing the endless sandwich into sheets of standard length, for example, 8 or 12 feet. This happens so quickly that the conveyor doesn't stop for a second. The cut sheets are now hard, but still very wet. They contain excess water that did not take part in the chemical reaction. It needs to be removed. Therefore, a special device flips the sheets and feeds them into the most large-scale structure in the factory, a multi-level drying kiln. This is a giant labyrinth consisting of several levels, each of which is a conveyor. The drywall sheets slowly move along these levels back and forth, traveling a path of several hundred feet inside this huge furnace. Hot air circulating inside gently evaporates the excess moisture from them. The temperature here is controlled very carefully. Only the free water needs to be removed without damaging the crystal structure of the gypsum itself. This process can take about an hour. At the exit of the dryer, the product we are familiar with appears, a perfectly dry, light and strong sheet of drywall. But this is not the end. The final stage is finishing. 2 finished sheets are stacked face to face. Their edges are perfectly trimmed to be even and clean. A paper tape with information about the manufacturer and product type is glued to the ends. After this, robotic manipulators with superhuman precision and grace lift the finished sheets and stack them in perfectly even piles on pallets. Each stack is wrapped in protective film, labeled, and sent to the warehouse. From there, it will travel to construction sites to become part of someone's home, having transformed from a simple gray stone mined from the earth into a smooth and cozy wall. Drywall production is like a barometer of the construction industry's health. When the economy is on the rise, people actively build new houses and renovate old ones, and the demand for drywall skyrockets. The factories that produce this product operate at full capacity, and the flow of trucks delivering the finished sheets across the country becomes endless. The heart of this production beats in unison with the rhythm of the real estate market. Geographically, this industry also has its centers. Although drywall manufacturing plants are located throughout the country to be closer to large construction markets, the mining of the main raw material, gypsum, is concentrated in certain states. The leaders here are states like Texas, Oklahoma, Kansas, Nevada, and Iowa.